Hi, in this video I'm going to prove that square root of 2 is irrational. Let's start. This symbol is the set of all positive integers. Known theorem. We have a theorem that we are going to use it. Any non-empty subset A of n has a minimum element. For example, if A equals 2, 4, 6, 8, etc., then A has a minimum element, which is 2. Any subset of n has a minimum element, and we can prove it using the completeness of the set of all real numbers, or there may be other proofs in other theories. Theorem: 1 is less than square root of 2. We prove it by contradiction. If 1 is not less than square root of 2, then square root of 2 is less than or equal to 1. So, if we multiply both sides by square root of 2, which is a positive integer, which is a positive real number, then we have square root of 2 times square root of 2 is less than or equal to 1 times square root of 2. So, this is 2, and this is square root of 2. So 2 is less than or equal to square root of 2, and we know that square root of 2 is less than or equal to 1, so 2 is less than or equal to 1, which is a contradiction. So we proved it by contradiction. So we proved the theorem by contradiction. Next theorem is what we're going to... Next theorem is what I intended to prove. Square root of 2 is irrational. I mean, it is an irrational number. We prove this by contradiction too. Suppose square root of 2 is rational, that is, it is not irrational. We are going to reach a contradiction. So suppose square root of 2 is rational, then there is some m, some natural number m, some positive integer m, such that m times square root of 2 is also a positive integer, a natural number. Why? Because we know that square root of 2 is of form m over n, where m is an integer, and then because we know that square root of 2 equals n over m, where m is a positive integer and n is an integer, because we have supposed that square root of 2 is a rational number. So so there is some m such that m square root of 2 equals some integer, z, the set of all integers, but we know that both of these numbers are positive, so n is a natural number. It is a positive integer. So there is some m in n such that m times square root of 2 is a positive integer, is a natural number. So this set a equals m in n such that m times square root of 2 in n is a non-empty subset of n. It is non-empty because there is some m such that m times square root of 2 is in n. So there is some n in n such that this is true, and that m is an element of A, so A is non-empty. And it is also a subset of n because all members of A are in n. Thus, A has a minimum element by the known theorem above. Any non-empty subset A of n has a minimum element. Let's denote this minimum element of A by A. a lowercase. So we denote this minimum element of A by lowercase a. This minimum element exists by that theorem, that known theorem. But let me edit this. Set b equal to this number. And that's right, we have. And here, let's write we have. Set or let b be equal to this number. A times this a times this, square root of 2 minus 1. But all of this equals a times square root of 2 minus a. But we know that this is a natural number, an integer, because a is in a. And so a times square root of 2 is a natural number. Also, a is a natural number because a is in a, and so it is in n. And we know that square root of 2 is greater than 1. So a times square root of 2 is greater than a. And so this number is positive. We know it is an integer and we know that it is positive, so it is a positive integer. Now we have b times square root of 2 equals, instead of b, we set this a times square root of 2 minus 1 times square root of 2 equals square root of 2 times square root of 2 equals 2. And square root of 2 times 1 equals square root of 2. So all of this becomes this, a times 2 minus square root of 2. And if we distribute, it equals 2a minus 2 minus a square root of 2. But this is also an integer. Why? Because 2a is an integer, and a square root of 2 is an integer because of this. A is in a, and so a times square root of 2 is a natural number, and so it's an integer. So all of this is an integer. But we know that b is positive, and the square root of 2 is positive, so all of this is positive, and so this is positive, and this is an integer, so it's a positive integer. That is, it is in n, the set of all positive integers. Thus, b is in a. Why? Because b times square root of 2 is in n. So, and we know that b is in n, and b times square root of 2 is in n. So b is in a. This is proved. Now, we know that. Now, because a is the minimum of a, by this, a is less than or equal to b. But what is b? B is defined here. But what is b? B is defined here. b equals a times parenthesis a times square root of 2 minus 1 in parentheses. A is a positive integer, so we can cancel a from both sides, and we get this. 1 is less than or equal to square root of 2 minus 1. And if 1 goes to the other side, we get this. 2 is less than or equal to square root of 2. And if we divide both sides by square root of 2, and if we divide both sides by square root of 2, we get this. 2 over square root of 2 equals square root of 2, and square root of 2 over square root of 2 equals 1. So we get square root of 2 is less than or equal to 1, but this is a contradiction by the previous theorem, which says 1 is less than square root of 2. This contradiction proves the theorem. Square root of 2 is irrational.